Welcome back, everybody. We are continuing with Chapter 7 notes on inclined or friction and inclined planes. And this is going to be example 7.5 involving Billy's toy box. You'll note there's no inclined plane right here, but what's interesting is there's an inclined force involved, which we've seen before, but this inclined force is going to affect normal forces and coefficients of friction and that kind of thing. So what we're going to do is just do part A of this problem right here and solve for the tension of the rope. All right. Now, before we talk more about that, let's just look at the problem itself. Okay. He has a 35 kilogram toy box. It's like 70 pounds of toys. That's a lot. But anyway, we have a horizontal floor, and this is interesting right here. Constant velocity. So there's no change in velocity, so therefore the acceleration is what? It's going to be 0, right? 0 meters per second squared. And so what's the net force on this toy box going to be in the direction of motion? Well, the net force equals mass times acceleration, right? And if acceleration equals 0, then the net force is 0 newtons right there. So what this is saying is that he's applying just enough force in this direction, in the parallel to the floor direction, for it to be moving constantly but not accelerating. Okay, so there must be some other force acting against him. And I think you probably know it's going to be friction, right? So he's really applying just enough force to overcome friction so it keeps moving but it does not accelerate. Because we said there is no acceleration in this box right here. All right, we are told the coefficient of kinetic friction, that's 0.15. And the rope makes an angle of 25 degrees with a horizontal, so that 25 degrees is our theta right there. Okay, so let's go ahead and start labeling these forces that are involved in Billy's toy box. First of all, the force along the rope. The question asks, what is the tension in the rope? Well, tension is just a force, and I'm going to call that F sub T right there. Tension force. We could call it T if you want. That's perfectly fine too. I'm going to call it FT. And that's what we're solving for. All right, so that's the big question of the day right there. All right, well, any force at an angle, we don't like it being at an angle. We like it being resolved into x and y components. And so this tension force, whatever that is going to have to be broken down into, I'll call that FTX, right? Which is really FT cosine theta. And there's a y component as well, right? We have ft, the y direction, of course, that's going to be ft sine theta, because that's how we get the y component of any vector. All right, and so these two forces, well, this one force is broken into two parts. The along the floor component and the perpendicular to the floor component, all right? Well, what else is going on right here? Well, we said before that there's probably going to be some friction force, right? And the friction force is acting, oops, I don't want to make that blue, I want to make that black. The friction force acts between the toy box and the floor and acts against the direction of motion, right? So he's trying to pull it, and the kinetic friction force is acting against him right there in the x direction, in the horizontal direction. All right, well, let's expand out a little bit what that friction force is. Right? How do we find the friction force between two objects? Well, we said that it's the coefficient of kinetic friction, right, which we are given, that's right up here, times the normal force. That is the force, you might say, of contact between the floor and the box. All right, so let's look at that now, okay? Well, we do have a normal force right here. There is going to be some sort of vertical normal force between the floor and the box, because somebody's got to support the box. And why does the box need to be supported at all? Because the box has weight. mg is usually it's one of the first things that we write. I'll clean that up a little bit. It's one of the first things that we write. mg, and everything that has mass is subject to gravity, has some sort of a weight force. So that's the force of the box down right there. But let's go back to this for a second. All right, our friction force. Our friction force is the coefficient of kinetic friction times the normal force. And in many cases, the normal force, the supporting force by the floor, is the same thing as the downward weight force, right? But it's not going to be the case this time, because in this case, the floor has some help. What is helping the floor support the box? Well, Billy is right here. He has a horizontal component of his tension force, but also a vertical as well. And so we can say for N, oops, I don't want to make that red. Oh, thank you. My wife just brought me some coffee. Isn't she wonderful? I'll write this in black here. For N, okay, well, you know what? In fact, I'll say not even for N, for the Y direction, for the Y direction, we can say the net force in the Y direction, first of all, is going to be 0, right? Because all the forces, this and this and this, have to balance out to 0 because it's not sinking into the floor, it's not rising up off the floor. But we can say in terms of components, the net force in the Y direction, component forces, is going to be the normal force up, right, positive, plus the tension force in the Y direction, I should write that in blue, but I'm going to keep it in black, minus the weight force, right? We have this acting up, and this acting down right here. So we can really say that if all that equals 0, right, all that is equal to 0, then we can really say that the normal force, so, that's a so right there, so the normal force is going to have to be equal to, let's see, negative mg minus ft in the y direction. Oh no, I'm sorry. Not negative mg, just mg, right? Because, sorry, let's back up here. If all this equals 0, mg goes over to the other side and becomes positive, and then the fty becomes negative. So the normal force is going to be mg minus the tension force in the y direction. All right, it's the difference because the normal force and this together are adding up to support the weight force right here. So the normal force is going to be less than it normally is. Why? Because Billy is helping the floor, right? He's applying a force up right here. So I'm not going to write it in right now. I'm going to shrink this down and we're going to do the problems together. But we are going to say that, and in fact, I'll circle this in orange. This right here is going to go in there. And that's going to make the difference. Since he is pulling upwards a little bit, he is actually making the friction force what? He's making it less, right? Because there's going to be less normal force. And now this coefficient always stays the same, but there's going to be less normal force, and so that there's going to be less friction between the floors. So he's actually helping himself by lifting up a little bit so that it makes it easier for it to drag it across the floor. All right? So the question is, at this angle, what is the force that he has to apply to the string with all these things in place? All right? And again, we're going to focus on what that normal force is when we get there. All right, let's take this. I'm going to shrink this down, all this down, and put it right up there. So it's really just a matter of summing up forces, right? Because, let's see, well, we'll write the net force in the y direction and in the x direction, right? The net force in the y direction equals 0 newtons, right? Because nothing's moving in the y direction. And also equals normal force plus tension force in the y direction minus mg, and all that, like I said, equals 0 newtons right there. Okay? So the normal force equals mg minus ft in the y direction. That's an equal sign there. All right? For the x direction, and this is really what we need to know. Well, this is not really what we need to know, but we need to use this to find out how hard he needs to pull. In the x direction is where we're going to be experiencing some friction, right? So we have to account for the x direction. So first of all, the net force in the x direction, what is it? Well, it's 0 newtons. Why is that, you say? Well, because remember we said at the very beginning, way up here, we said that since it's not accelerating, there's a constant velocity, then that means the acceleration is 0, and so there's no net force in the x direction. It's moving, but it's not accelerating, so therefore there's no net force. All right, that's helpful. But also, let's sum up the component forces in the x direction, COMP. There we go. All right. Well, we're going to call his direction positive, and we're going to call the opposite direction negative. So I'm going to actually start color coding this now, so you can tell everything apart. We have his tension force in the x direction that he's applying, right? And we have, acting against that, we have the friction force, the kinetic friction force that is acting against him. All right, and all that, like we said, equals 0 newtons, because that is also true. All right, so let's take this now. Let's take these statements and expand them out a little bit. All right, because we can be more detailed in that description and in that description as well. So let's, I'm going to go back to green again, at least temporarily. Our tension force in the x direction is Ft cosine theta, right? Because we said this is true right here. And the friction force in the x direction, well, that's going to be, well, there's a minus sign here, mu k times the normal force. And all that equals 0 newtons. But remember, we said the normal force is going to be something special. Well, not special, but it's going to be a little bit more complex than it normally is, because we've got Billy helping the normal force right here. And so let's expand these out again even further. Well, actually, the x is going to be the same. We can say the tension force in the x direction is going to be Ft cosine theta. But the kinetic friction force is going to be mu k times what is n now? Well, we said that it's going to be mg minus Fty. All right, mg, the weight force, minus the force that Billy is applying. You know, I should make that blue. I am going to make that blue. The force that Billy is applying to help the floor. Tension force in the y direction. Like so. All right. Well, even that can be expanded out, right? Because, first of all, we've got to solve for that Ft right there. So we've got to make a statement that involves just Ft. Let's write it out one more time, and then I think we'll be able to start using algebra to solve. Ft cosine theta, that's the x direction, the force in the x direction that Billy is applying, minus the friction force. What is that? We've got mu k times mg minus what? Tension force in the y direction, and that is Ft, not cosine theta, but sine theta, right? Ft sine theta, and then we can close our brackets right there. And now I think we're ready to solve for what? To solve for Ft, right? Got to remember always what we're solving for. Oh, by the way, I didn't really complete that statement right there. It's not an equation without an equal sign. Equals 0 newtons. All right. So let's solve for that Ft sine theta. First of all, I'm going to, let's see. Well, we want to get these two FTs together, right? And this is actually a kind of a question that many people have come to me and asked me about. Like, how do you get two, well, it's one unknown, but they're in two different places. How do you get them together right there? Well, we're going to need to do some kind of creative factoring and distributing, and that's what we're going to start with right now. We cannot combine these two FTs, even though they're different colors, they're the same FT. We can't combine them until we break apart this this parentheses right here, and that's what we're going to do. All right. So what I'm going to do is, first of all, I think to make this easier, I'm going to take this whole thing, this whole statement, that I'm going to add it to the other side. All right. And the other thing is I'm going to just write it in black from now on. So I'm going to take all this, add it to the other side, so we get rid of some negatives right there. So we're going to have Ft cosine theta equals UK times mg minus Ft sine theta. All right. Now that'll make this a little bit easier. It's still the same equation, but I just kind of cleaned it up a little bit, got rid of some of those minus signs right there. So let's look at just this. We want to get, it seems like we move these FTs further away from each other, and we did temporarily, but we want to get these FTs together eventually, which means we've got to break open this parentheses here, which means we should distribute this mu k. Distribute that to that right there. So that's what we're going to do. So we have ft cosine theta equals mu k mg, all right, minus mu k, that is our coefficient of friction, ft sine theta. All right. So that helps us a little bit, because now we're one step closer to getting these FTs next to each other. Well, let's, I'm going to shrink this down a little bit more. Oh, I can't do that. That's just going to be messy if I try to do that. I'm just going to continue on the other side right there, and I think we'll be able to do that, even though it would be nicer to have a little bit of extra space. Draw a line straight down like that. All right, and so we're going to move this up here. And so what's the next step? Well, let's start getting these FTs next to each other, because we couldn't before because they were locked up in a parentheses, but now we can. So we're going to take this, and we're going to add it to the other side. All right, so we've got ft cosine theta plus mu k ft sine theta equals mu k mg. All right. So we've gotten them to the same side, and we've gotten that other mu k mg away from them. Now what can we do? We still have two of these FTs right here, but the good news is that all statements on this side have FT in front of them. So what are we going to do? We're going to factor them out. All right. So factor out that FT right there, and then we have cosine theta plus mu k sine theta. All that equals mu k mg. All right. I think you know the last step right here, and that is to take all this in the brackets right here and just divide it down, and that's what we're going to do. So our tension force that Billy has to apply is going to be our coefficient of kinetic friction times mg over cosine of theta plus mu k sine of theta. And that's what we're going to do. All right, so I'm going to pause this for just a second. I'm going to do my calculations. You can do yours. Go ahead and just substitute in. I'm not going to write them in, but I know you can. And I'm just going to do that separately. In just a second, I'll be back, and I'll have the answer. Hopefully, you're the same thing. All right, assuming you plugged in all your values correctly and you did the right order of operations, hopefully you get the same thing that I get, and I get the tension force that Billy has to apply is 53.1 newtons. That's what we get. So that's assuming you plugged and chugged and did that all correctly. So that's Billy's toy box. The key here is the fact that since his applied force is helping the floor, or helping the floor support the toy box, then the normal force is going to be less. Less normal force means less friction force. And so if we account for all those things, we can solve for exactly what Billy has to apply to that string in terms of tension. So that's example 7.5. I hope that helps. If it doesn't, please let me know if you have any questions about this. But in the meantime, thanks for watching, and I'll see you on the next one.